All right. So today we are going to talk about synchronous machines. And I hope to get through the basic operation of both generators and motors today. And then in Thursday's class meeting, we'll talk about all of our power and torque relationships for all that kind of good stuff. And then we'll be done with synchronous motors. Then we have our Mardi Gras break. Then we're going to have two class meetings of DC machines, and then we're done. So on the syllabus, it had 3 days for synchronous machines and 3 days for DC machines, but because of the winter event and all that kind of stuff, I'm trying to just compress things so that we finish at the same time. All right, so let's start with a synchronous generator. So I'm going to draw a picture here. It's going to be kind of awful, but it'll be okay. Awful in as much as I can't draw, not that there's a whole bunch of things going on. So we have these two concentric circles here. And in a synchronous machine, this is what is commonly called the armature. And it simply serves as the stator of our machine. Okay. So because it's the stator, it's going to look extremely similar to the stator of a three-phase induction machine. So up here will be my A phase coil. Down here will be my A prime. Then I'll have my B, and across from it, my B prime. Down here will be C, and up here will be C prime, where each of these represents what's called a phase winding, much like we had in our induction motor, right? So the stator is effectively the exact same thing as we had in the induction motor. We've got three different phase windings, one for each phase of our three-phase machine. And then our stator just has a fancy new name and armature for reasons that I can't remember off the top of my head. Okay. Now, the rotor part is going to be appreciably different, right? So in an induction machine, we had a squirrel cage rotor where we induced AC voltages and currents. In a synchronous machine, we are going to, instead of having an AC electromagnet, we're going to have a DC electromagnet, okay? So it's going to look something like this. So here in the middle, I'm going to put my shaft, and it's rotating with an angular velocity of omega. Let me put a note over here. This thing in the center is just the shaft, okay? And then inset a little bit. We're going to have this shape. And so this big thing right here is spinning, okay? So these boxes that I'm putting X's in right here, these represent the DC field windings. So we have some DC current that's applied to the windings on our rotor, which is commonly called a field system in one of these devices. So if I have a DC current flowing through my field windings, what kind of magnetic field are my field windings going to generate? Also going to be a DC quantity. So instead of having like a kind of a pulsating magnetic field like we saw in a induction motor, we're going to have a constant magnetic field. And so realistically, this thing here in the middle just looks like almost a permanent magnet, right? So we are going to have some associated north pole of the magnet and some associated south pole. And these are typically called the field poles, okay? So we have a DC electromagnet that's spinning inside of a three-phase stator, okay? So when a field current flows through the rotor windings, or our DC field windings, and the rotor is turned in a clockwise or counterclockwise direction, we wind up getting a revolving magnetic field established in our air gap. Okay. So like the picture that I have right now, the magnetic flux that's passing through coil A is effectively at its minimum at this pictured position. And I say that because the field lines are oriented vertically and the phase winding forms a loop effectively vertically. And so there's not any magnetic flux that's passing through the surface that's bounded by that coil because it's all in the same plane as the coil itself. But when the rotor turns, so if it were to turn clockwise or counterclockwise 90 degrees, our electromagnet field would be oriented horizontally, and our coil is effectively oriented vertically, so we're going to see a very large magnetic flux between it. And as it spins, the flux seen by the phase winding is going to go from 0 to its maximum value, back down to 0 to its minimum value, back up to 0, and so on and so forth. So we have a revolving magnetic field, much like we had earlier. What we're going to see is that as that flux changes, we are going to have an induced voltage drop across each of those phase windings, okay? So those voltages are going to look something like this. So I'm using the E for induced. So the voltage drop induced across coil A to A prime as a function of time is going to look like some maximum value of the induced voltage, which is E max times cosine of omega t. And then across our B phase winding, we'll have E BB prime of t is going to look like E max times the cosine of, sorry, I don't need this parentheses out here, omega t minus 120 degrees. And it's minus 120 degrees because our coils are physically 120 degrees away from each other around our armature. And lastly, ECC is going to be E max cosine of omega t minus 240 degrees. So effectively, if we spin this DC electromagnet inside of this three-phase stator, we wind up generating a three-phase voltage, which is exactly what we would expect a three-phase generator to do. It's going to generate three voltages, all that are 120 degrees out of phase with each other, so that it represents a balanced three-phase voltage source. Okay. So now let's talk about the peak value of the induced voltage. So Emax is omega, the speed at which our shaft is spinning, times n, the number of turns in the phase winding, times phi b, which is the flux per pole due to our field current. So let me write those things down really quickly. So omega is the speed or angular velocity of the shaft. This n is the number of turns in a particular phase winding. And then phi b is the flux per pole caused by IF, where I is the current and the subscript F is just field. Okay. So it's dependent on the amount of DC current that we supply into the windings on our rotor. Now, this is the equation for windings distributed in a single slot. If we distribute our windings in multiple slots in the stator, we're going to have this relationship. So same omega, same n, same phi b, but now we're going to have this factor of kW, where this kW factor is what's called the winding factor of the stator, and kW is always less than 1. So effectively, instead of having a nice tight coil physically located in one specific place on the stator, we would distribute the coil around the entire length of the stator. And that causes this factor kW a little bit less than 1. So let me just put a note here. For windings distributed over multiple slots, which is actually way more common than having our winding in a single slot. And then lastly, we can just replace omega with 2 pi f so that we know that it's effectively, the field is related to the frequency, the linear frequency of our system. So if we use this relationship for Emax, we can rewrite our induced voltages in the stator windings as E A to A prime 2 pi F N phi B kW times the cosine of omega t volts and so as an RMS voltage, this is just going to be 2 pi over root 2 F N phi B kW volts RMS. Okay, so that's just our magnitude of our RMS voltage. All I'm doing is dividing the magnitude of the sinusoidal voltage divided by the square root of 2, because we know that we've got a sinusoid and the effective value of a sinusoid is just divided by the square root of 2, right? So that's what our RMS voltage is going to look like. And then we can follow through with the subsequent phases. So E B to B prime is going to be effectively the exact same thing. 2 pi F N phi B kW cosine omega t minus 120 degrees volts. And I'm just going to say here that the RMS magnitude voltage is the same in the B phase as it is in the A phase without having to write down that equation over and over and over again. Yes. Okay, so over here on the left-hand side, we have a time domain representation, right? Over here on the right-hand side, we're just looking for the RMS value. So this isn't quite a phasor because we also threw away the phase angle, but if I put angle 0 on this guy, this is just an RMS phasor voltage. If I put angle negative 120 degrees on this guy, this is just an RMS phasor voltage. So we're never going to actually do any of the circuit analysis in the time domain because it's a huge pain in the ass. All of the circuit analysis for what's going on is going to be using the RMS values because we have a three-phase system. So I'm just transitioning us over from looking at the time domains, the time varying voltages, and saying we're now going to look at these as if they were an RMS voltage because that's exactly what they are. Does that clear things up? Okay. So we're not throwing it away per se. We're going from the time domain, which is very difficult math, trig relationships, all that kind of stuff, to the RMS phasor domain where everything is algebra and everything doesn't suck. So. And then similarly, ECC will be 2 phi F N phi B kW cosine omega t minus 240 degrees volts. And so the magnitude of this RMS voltage will be the same as the other two. So from this, we can actually see three things, okay? Our induced voltage is dependent on one, the speed of rotation, which is omega or F. Two, it's dependent on the flux generated by the field windings, which is just phi B. And lastly, It's dependent on the construction of the machine itself. Because we have some dependency on N, the number of turns, as well as KW, our winding factor, right? So three different things contribute to the size of the voltage that we are going to see produced by our generators, right? And the magnitude of the voltage is linearly proportional to all three of these things. So if we spin our rotor faster, we get a larger voltage. If we put more turns, we get a larger voltage. If we drive more current through our field windings, phi V will increase and we get a larger voltage, right? So it's just a simple relationship of the things that we can change in order to get larger voltages out of our system, okay? So let's look at an example problem really quickly here. Okay. So let's say that we have a two-pole, three-phase synchronous generator. Has a rotating flux of phi B is equal to 51.6 milliweber. The number of turns in each phase is N is equal to 20. And the shaft speed is 3,000 RPM, which just for the sake of argument here would be frequency of 50 hertz. And the stator winding factor KW is equal to 0.96. And I want us to determine the RMS phase voltage of the generator. So how large of a voltage will it provide? So our RMS voltage is literally just going to be 2 pi times our frequency times our number of turns times our flux times our winding factor, right? So that's going to be 2 pi times 50 hertz times 20 turns times 51.6 milliwebers times our winding factor of 0.96. Okay. Let's look at these units just really quickly here. Okay. So how many of you guys remember what the units for a Weber are? What does it break down into? Volt second. Just a volt second. Yep, so a Weber is just a volt second, okay? So we have volt seconds multiplied by hertz, where a hertz is just a per second. So the only units that we have in here is volts times seconds divided by seconds is just going to give us volts the output, right? So pretty straightforward conversion of things here. So 100 pi, which is just 2 pi times 50. And then we have 20 times 51.6 times 10 to the minus 3 times that winding factor of 0.96. I did miss one thing here. I forgot my square root of 2. So I apologize for that. So let me divide this thing by root 2. And we wound up getting 220.083 volts RMS. So 50 hertz is the typical frequency used for generators in Europe. Here in the US, we use 60 hertz. So do you think we would get a larger voltage here in the US or a smaller voltage? A larger, right? Because the frequency is faster. What should the answer for the US voltage be? Something like that, but I would just multiply this by 6/5 and call it a day because that's the change in my frequency, right? So that's multiplying by 60 hertz to give us the American dividing by 50 hertz to get rid of the European. So it's just an easy scaling factor, right? So multiply this by 6/5, 264.099. So I'm going to put here for EU, and then down here, 264.099 US at 60 hertz. Means if we were using this here in the States, we might want to back off the field current just a smidge to bring that voltage down to the 240 that we're used to. All right, so I think we have an okay understanding of why the voltages are induced. So we've got a DC magnet that's rotating. The flux through each of the stationary coils is going to change as that magnetic field spins around. We are inducing voltages based on this equation. All of that's fairly straightforward. Now let's take a look at our equivalent circuit. So I'm going to break this into two parts. I'm going to have my field circuit that is effectively what's going on with my rotor. Okay. And so that's going to look something like this. So across these terminals, I'm going to apply a voltage VF, and this is a DC voltage. Here, I have effectively a rheostat. It's just a variable resistor that I'm going to call R sub ADJ. So I can just adjust this resistance value to control the amount of field current that's actually sent to the windings. where my field current is this current IF. Then I have a resistance RF like so. That's just the resistance of my field windings themselves. Okay, so it's a coil. It's going to have some finite resistance. And then my coil is also going to have some inductance. So I'm going to call this JXF, and I'm going to make a little note here just inside. This is a rotating field caused by the physical rotation of the shaft by what's called the prime mover. Okay. So the prime mover is what connects to the shaft and causes it to spin. So this is the field side of things, and this is, for the most part, just a DC circuit. Okay. Now, let's look at the armature or stator side of things. And I'm actually going to have three different circuits because I've got three phases. So they're all going to be largely identical, but we're going to have one for each phase. Okay. So let me just put over here armature circuit in parentheses stator. And so should have something that looks like this. Make this a little bigger. So this voltage EA is the induced RMS phasor voltage that we just figured out how to calculate. Okay. Then we're going to have some resistance RA, where this resistance RA represents the AC resistance of the stator winding. Okay. I'm going to write this down in a moment. But the AC resistance of the stator winding is a little different than the DC resistance of a winding, right? So let me come down here really quickly and just write that in. This is typically 1.6 times larger than the DC resistance the winding. Does anybody know why that is? You guys heard of a thing called the field, or excuse me, the skin effect before in any of your physics classes or anything like that? Okay. So I don't want to get too granular in detail, but when you have a conductor and it's carrying a DC current, the current uniformly distributes itself through the conductor. So the current density is a constant thing throughout the conductor. When your frequency increases, what you'll find is that the current actually only passes through the edges of the conductor. And the higher the frequency you're at, the thinner the surface is that the current flows through. So let me sneak a little picture in. Let's do it down here. Okay. So here's a cross section of a conductor. At DC, all of that area is used. At AC, for 50 or 60 hertz, we'll see that most of that cross-sectional area is, but not all of it. As we get higher and higher and higher in frequency, that'll be less and less and less of the actual conductor's cross-sectional area is actually used to carry current. Well beyond the scope of this class or anything like that, but at gigahertz frequencies, which are typically used in like microwaves and things like that, we actually only see that like around 1%. So it's just all of the current is effectively confined to the surface. So very regularly, instead of using conventional wires, we use what are called microstrip lines. So if you ever looked at the traces on a circuit board, that's usually an example of a microstrip line, where it's wide, but very, very thin because you only need a small amount of surface area to carry the current, and you make it wide enough so that it doesn't heat up so much that it melts. So anyway, that's why circuit boards are designed the way they are, is because they're designed to be carrying AC currents. All right, so we've got our AC resistance of the stator winding. I bored you guys with a little information about the skin effect in AC circuits. Then we have this impedance JXA. So this reactance represents the self-inductance of the stator windings. And now we're going to have a separate reactance, JXAR. So this is the armature reactance, and I know that's a mouthful, okay? So let me tuck it in over here. So because our armature is carrying an AC voltage and current, it's also going to generate some amount of magnetic field, right? Anything that's carrying a current generates a magnetic field. Well, the magnetic field of the armature or the stator winds up interacting with the magnetic field of the rotor, and that interaction causes that reactance. Right, and then over here, we just have a terminal. And so across this terminal, I'm going to have a voltage, which I'm going to call V phi A. And all I mean by this is the voltage drop across the A phase of the terminals of our generator, okay? So EA is an induced voltage. VA is the voltage that we actually physically have access to when we connect stuff to the generator itself, okay? And then over here on the right, to complete the circuit effectively, I'm just going to put some load. And now all I'm going to do is replicate this 2 more times, once for the B phase and once for the C phase. So all 3 of our 3-phase circuits are going to look identical. So this is going to be our terminal voltage for the terminal voltage for the B phase. And then some connected load. And oh goodness. Here's our C phase. V phi C load. All right, sorry it got a little busy and messy down there. I didn't give myself enough space. Okay. So this is what our equivalent circuit looks like. Now we're going to make really one small modification, and then that's the only modification that we're going to need to make. So one thing that I want to point out here, at least to me, the equivalent circuit of a synchronous machine like this one is actually a little bit easier to wrap your head around than the equivalent circuit of an induction machine, because we have two separate systems, right? They are not tied together effectively with an ideal transformer or anything like that. We've got a DC circuit on one side and an AC circuit on the other side of things. So largely, if we're looking at a generator, we're actually just going to be focusing on the AC circuit side of things, because everything that's going on the left-hand side or the DC side is just we're passing a current and we're spinning. And then the interesting stuff that's happening is all on the AC side. So we can just use simple RMS phasor voltage analysis techniques to see what's going on. Conversely, if we're operating as a motor, then all of this stuff is the boring stuff. We just apply electrical power over here. And then the interesting stuff, all of our motion is happening on the DC side of the circuit. So because everything is so compartmentalized, it's a little bit easier, in my opinion, to analyze and understand what's going on. All right, so going back around to our simplification, typically speaking, these two reactances might be lumped together as JXS, where this is the synchronous reactance. So instead of having two reactances to deal with, we just lump it together to call it one reactance. It doesn't really make things a whole heck of a lot simpler, but it means that we can convey the same information with less space. Okay. So if we were to look at just one phase of our stator, right? So let's look at the A phase, for example. It would be something like this, where we have our RMS phasor voltage EA, our resistance RA, our reactance JXS, our terminal voltage V phi A, and then our load over here. We can actually observe a couple of things, okay? So if our load exists, meaning that we physically connect our generator to something, the voltages EA and V phi A are going to be two different things because there's going to be some voltage drop across our resistance RA and our reactance XS, right? So generally speaking, let me put a current here. IA. Our terminal voltage V phi A is equal to EA minus IA times RA plus JXS. I'm going to make a note here under load. Okay. So from this relationship, we can see that for loads with a lagging power factor, the magnitude of our terminal voltage will be less than the magnitude of our induced voltage. So this occurs because it takes more current to keep our terminal voltage constant when we have a lagging power factor. Transversely, for loads with a leading power factor, the magnitude of our terminal voltage should be greater than our induced voltage. So we typically call this condition, sorry, the screen scrolled on me, over excitation, and this condition under excitation. So all of this right here just serves to us as kind of a sanity check in our analysis, right? If we are conducting our generator to some sort of industrial load that's operating at a lagging power factor, and we calculate that the terminal voltage at our generator is larger than the induced voltage, we know we've made a mistake somewhere in our analysis and vice versa, right? So this is just kind of a sanity check thing to make sure things are working out correctly. All right, so one last thing here. There is going to be a phase difference between our terminal voltage and our induced voltage, right? Because, and that phase difference is going to be dependent on how large RA is in compared to XS, all that kind of good stuff. So we can define a power angle or torque angle as lowercase Greek delta. And this is just the angle of our induced voltage minus the angle of our terminal voltage. This is commonly called the power or torque angle. And just as a heads up, this is literally the exact same lowercase delta angle that we were talking about when we were talking about electromechanical energy conversion in cylindrical machines like 3 weeks ago at this point. It's all coming back around. So let's work another example problem. You guys like numbers? So let's say that we have a three-phase 13.2 kilovolts. And I'm going to put a note here. Line to line. Actually, RMS. 13.2 kilovolts RMS line to line voltage. 60 hertz. 50 megavolt ampere. Synchronous generator. Has a winding resistance of RA is equal to 0.15 ohms per phase. And armature reactance of XAR is equal to 2.19 ohms per phase. And the leakage reactance, which is just X sub A, is 0.137 times the armature reactance. If the generator is delivering full load current at rated voltage, at a power factor of 0.8 lagging, determine A, our synchronous reactance, X sub S, B, our full load current, IA, our induced voltage, EA, and our power angle, delta. All right, so how do you guys think we are going to determine any of these quantities? Yeah, that's it. That's part's easy, right? So our synchronous reactance XS is just XA plus XAR. Well, we were told specifically that XA is just 0.137 times XAR. So that's going to look like 0.137 XAR plus XAR, or 1.137 XAR. And since XAR is given to be 2.19 ohms per phase, that comes out to be 2.490 ohms. So that's it right there. Pretty simple and straightforward. We're going to use it in a moment with the equivalent circuit to figure some other things out. So now I want to find our full load, or effectively our rated current, okay? Full load current. So anybody have any thoughts on how I might determine that based on the information that we have? And let's scroll up here to look at what information that we have. So what does that 50 megavolt amperes up there mean? So that is the apparent power that this generator is rated for, right? So we have apparent power, and then we also have power factor. So if I have apparent power and a power factor, that's enough information for me to determine the complex power. And then the complex power divided by the voltage should give me the current that's flowing in the device, right? Glossing over some of the fine details like conjugates and all of that kind of stuff, so we'll sort that out in a minute, but that's how we're going to look at this thing. So the complex power supplied by our generator is going to be 50 megavolt amperes with a phase angle of the inverse cosine of 0.8, which should come out to be 50 angle 36.870 degrees megavolt amperes. For those of you that need quick refresher, our power factor is defined to be the ratio of the average power to the apparent power, and this is also the cosine of our power factor angle. So I just manipulated this relationship in order to get the magnitude of our complex power, which we were actually already given, so I didn't have to do anything for that. And then the inverse cosine of our power factor angle, the inverse cosine of our power factor should give us a power factor angle of 36.870%. So all relationships that we've seen before. Okay. So using this, we now need to figure out what our current is. Okay. So since this is a three-phase generator, we could also say that S-gen is going to be equal to the square root of 3 times our line voltage magnitude times, actually, our RMS phasor line voltage and the complex conjugate of our RMS phasor line current. So by manipulating this expression, our current IA should just be S gen divided by √3 times our line voltage. And then I conjugate this guy. So the reason why I'm using the square root of 3 relationship here, as opposed to the 3 times voltage times conjugate current, is because we were explicitly given a line-to-line or delta connected voltage. This thing was outputting, right? So if instead I were having a Y-connected voltage, or if I was given the Y-connected voltage, this relationship would be modified where that square root of 3 would then look like just 3. Use that voltage. So I just want to be clear about that. So from here, this is going to look like 50 angle negative 36.870 degrees megavolt amperes divided by the square root of 3 times 13.2 with an angle of 0 degrees kilovolts RMS. So I have a quick question for you guys. Why is the sign on the angle 36.870 degrees negative here? Conjugate operation, right? So this is a silly question, but why isn't the sign on the 0 changed? Because 0 and -0 are the same damn thing, right? So whenever we take the complex conjugate of a fraction, we technically need to take the conjugate of the numerator and the conjugate of the denominator. Because we're assuming that our voltage has a phase angle of 0. That's why it's not having any impact there. So if I do the math here, what happens when I'm going to divide megavolt amperes by kilovolts? What should my resulting number be? Or what should the units be? It won't be just amps because megavolts is 10 to the 6 and kilovolts is 10 to the 3. Right, so it'll be watts. So if I just do this math like this, I'm just going to get an answer in kiloamps, which can be okay, nothing wrong with it. I just want us to be consistent and clear about what units we're getting, right? So this will come out to be 2.187 with an angle of negative 36.870 degrees kiloamps RMS. So that is a pretty aggressive amount of current. Now let's talk about our induced voltage, right? So looking back up here, I went too far, at our single phase equivalent circuit. And I've already given us this handy dandy relationship. We are trying to solve for this induced voltage EA. Okay. Now, this is our single phase equivalent circuit per phase, meaning that it's measured from phase on the positive polarity terminal, so the A phase on the positive polarity terminal, to neutral, right? The voltage that we just used in our previous calculation was a line-to-line voltage, not a line-to-neutral voltage. So we do have to pay attention to things like that so that we don't get stuff mixed up here, right? So if I were to effectively move this IA times RA plus JXS over to the other side, I could solve for EA directly, but we need to be careful about what voltage we're putting in for our phase voltage there. So we're going to have the voltage drop across the A phase plus IA times RA plus JXS. So how am I going to convert my 13.2 kilovolts line to line to a line to neutral voltage? What was that? So not multiplying by 3. Divide by the square root of 3. So that's going to look like 13.2 kilovolts RMS, 13.2 angle 0, to be formal about this, divided by root 3. Then I have 2.187 angle 36.870 degrees kiloamps RMS times 0.15 plus J 2.49 ohms. I get 11.901 with an angle of 20.457 degrees. Now I'm looking at these notes from last year, and I'm a little bit concerned that I actually made a mistake in this calculation. So let me explain what mistake that I think I made. I divided 13.2 by root 3, which will give me the magnitude of my line-to-line voltage, but that's actually going to screw up the phase angle. Just as a brief reminder, if you guys will indulge me on a quick review here. So a three-phase voltage source should look something like this, where here's our neutral connection. This is the A phase, the B phase, and the C phase. And this is the voltage measured between the A terminal and the neutral terminal. This is the voltage measured between the B terminal and the neutral terminal. And this is the voltage measured between the C terminal and the neutral terminal, right? And then this voltage right here, let me do it in a different color. Is the voltage measured between the A terminal and the B terminal, right? So we can see a distinct difference between the line-to-line voltage, which is VAB, and the line to neutral voltage, VAN. And that's what we were just trying to do a conversion between. So I can note a couple of things here really quickly, right? So VAB is going to be VAN minus VBN by doing Kirchhoff's voltage law around the top loop, right? So that's just around this loop right here. I know that my B phase should lag my A phase by 120 degrees, right? So this should actually look like VAN minus VAN angle, excuse me, one angle negative 120 degrees. which is going to wind up looking like 1 minus, let me put this in complex math, 1 minus 1 angle negative 120, which should come out to be √3 angle 30. So this is VAN times √3 angle 30 degrees. So to me, if I was being incredibly formal about this, I would actually wind up putting that angle 30 degrees there. And I think it is actually going to have an impact. Because typically speaking, adding a magnitude plus a magnitude is not going to give you the correct magnitude, and that's what I'm worried about. So I'm going to recalculate this really quickly just to be more formal. Like I said, I think I just glossed over something last year that I should have been more aware of. √3 angle 30 plus 2.187 angle negative 36.870, 0.15 plus 2.49. Okay. So pretty different number. So let me fix that. .136 with an angle of 1.974 degrees kilovolts RMS. So that phase change that happens when we go from a line to line to a line to neutral wound up giving us a voltage that is about 1 kV less in magnitude than if we had neglected it, right? That's a pretty appreciable error in our calculation. So from here, how do we figure out our angle delta? Right. So this is the angle of our induced voltage minus the angle of our phase voltage. Well, the angle of our induced voltage we just found to be 1.974 degrees. What should the angle of our phase voltage at the terminals be for the A phase? We have it effectively right here, right? Let me just put a little box around this. So if I have 13.2 angle 0 divided by √3 angle 30 degrees, whatever angle I get from that math is the angle of the phase voltage, which is going to be negative 30 degrees, right? So this should be minus negative 30 degrees, comes out to be 31.974 degrees. So when we talked about transformers at the very beginning of class, we introduced a concept called voltage regulation, right? So voltage regulation was effectively how much do we let the induced voltage change in order to maintain a constant voltage at the output. And that's exactly what goes on in a synchronous generator as well, right? So we can define voltage regulation as follows. So voltage regulation is going to be the magnitude of our induced voltage, sorry, that should be an RMS, minus our phase voltage divided by our phase voltage. So if we were to calculate the induced voltage from the previous example, this would look like 10.136 kilovolts RMS minus 13.2 over the square root of 3 divided by 13.2 over the square root of 3. And this should come out to be 56.160%. All right. So let's talk very briefly about synchronous motors now, and this will literally be very brief, like 10 to 15 minutes tops, and then we'll be done for the day. So if we look way back up here at our circuit, let me put a note here. Here's our current IA. If we were to operate this device as a motor instead of a generator, what do you think our change would be? Right, so instead of having a load on the right-hand side, we would have a source. So all that's really going to do is just change the direction of that current IA. That's it. So in a synchronous motor, our AC circuit is going to look something like this. So here's RA, here's JXS, now we are applying the voltage across the terminals, and our armature current is flowing in the opposite direction, so that we can see the voltage drop across our terminals is simply the induced voltage plus IA times RA plus JXS. Literally the only difference that we need to look at. Our current's flowing in the opposite direction because power is flowing in the opposite direction. Okay. So now let's talk about something conceptual here really quickly. Starting a synchronous machine. Okay. So in an induction machine, we know that when there was a difference in the speed of the rotor and the stator's excitation, a torque was generated on our rotor, which caused it to start spinning, okay? Well, unlike an induction motor, a synchronous motor is not a self-starting device. So it's not going to cause itself, its own rotor to start spinning, okay? So if the rotor fields are excited by the field current and the stator terminals are connected to an AC supply, what we're going to see happen is that the motor isn't going to start turning, it's just going to shake, okay? This is because the stator field is moving so quickly compared to the rotor that it literally can't catch up. So all it can do is just vibrate, right? So we're talking about exciting the stator windings at 60 hertz, 50 hertz, or something like that. So 60 cycles per second. We've got DC excitation on the rotor windings. There's just such of a mismatch that effectively the motor doesn't really know what to do. And so all of that power going in has to manifest in some way, and it's just going to be mechanical vibrations, not any spinning or anything like that. We don't have enough going on to get any torque, okay? So in order to start a synchronous motor, we can do one of two things, okay? So the first thing that we can talk about is using a variable frequency supply, or what's commonly called a variable frequency drive, which you guys might have some experience with, right? So starting with a VFD. Can't spell start. So we might have something like this. So over here on the left is the terminals of our three-phase supply. And this first box is going to be a frequency converter. So we input some frequency control signal, and we input some voltage controls. So just because we have 60 hertz is the what our three-phase supply is operating at, our frequency converter can operate at very, very low frequencies, close to DC, and then we can effectively just turn that up slowly. And so we're going to see that voltage and frequency, effectively message signals, get sent to the synchronous motor. As well as our field current. So the frequency converter allows us to have a stator field that is rotating very slowly, which allows the rotor poles to follow the stator field. And then the frequency is gradually increased until the motor reaches the desired speed. So a system like this actually allows a synchronous motor to operate at literally any speed that can be provided by the variable frequency converter, right? So instead of always being a multiple of 3,600 RPM, or in the US, or 3,000 RPM in the EU, we can just spin it at any speed we want. Typically speaking, these variable frequency drives are usually kind of expensive, right? F control and V control. So we have control over both the frequency and the voltage that's being applied to the synchronous motor so that we can bring it up to speed safely. Because if we have the frequency too high or way too high of a voltage at way too low of a frequency, we can burn things out. So another way is effectively to start it just like an induction motor. And let me see if I can find a picture of this. Effectively, on your synchronous machine's rotor, it might have a small squirrel cage that's used for starting it as an induction motor. And then once it gets up to speed, that really does, it effectively gets overwhelmed by the synchronous motor part of things, right? So let me see if I can find an image. So actually, this is a good one right here, right? So this picture right here would be what a 4-pole rotor would look like. And then each of the poles has bars, just like the bars in a squirrel cage induction rotor. So that it allows us to have somewhere to generate some torque, even when there is a large difference in the frequency of the stator excitation and the rotor excitation. And so what these are going to do is they're going to allow torque to be generated on the rotor so that it's going to start itself. But if our speed ever falls off, so if the speed of the rotor ever doesn't match our synchronous speed, these guys are going to kick back in and kick the rotor's speed up to make it catch back up to the synchronous speed. So it's also got a built-in mechanism to effectively keep it locked in to the synchronous speed of the stator excitation. So this is what you will typically see in most applications where you only want the device to work at a single speed. So instead of using a VFD, we use these damper windings or damper bars to effectively bury almost a small induction machine inside of our synchronous machine to make sure that things keep rotating the way that they're supposed to. All right, so that's all that I wanted to talk about for today. So on Thursday, we'll go over power and torque relationships and all that kind of good stuff, and then we'll be done with synchronous machines. Definitely going to be a homework. Oh, no homework for today. That's correct.
I would hope there would be homework.
Yeah. Well, feel like you guys going into an exam with no homeworks would be less than great for you.